All right, hey everyone, welcome back to our lecture series for linear algebra. So today we're starting chapter 5, which we'll be talking about orthogonality. So this is a throwback, and this will be the topic for all of chapter 5, but we're going to dive really deep into just what is orthogonality. What does it mean for things to be at right angles to one another? Whatever that, in like high dimensional spaces and stuff. Right. So, just remember from like chapter 1, we had the definition of orthogonal. So two vectors were said to be orthogonal if their dot product was 0. And we showed that geometrically that was the same as being at like forming a right angle through the origin for two vectors, right? So we just want to generalize that. We want to say like, well, what if you had more vectors in a higher dimensional space, right? So a set of vectors, v1 up through vk and Rn, is said to be an orthogonal set if the pairwise dot product of any two vectors in the set is equal to 0. Obviously, don't take the dot product of a vector with itself for this definition, right? Okay. First of all, first example we need to see is that any subset of the standard basis for Rn is orthogonal. Right, that's just saying that the coordinate axes in R2 make a right angle, or the coordinate axes in R3 make a right angle, and so on, right? Or any two of the coordinate axes, and so on, right? But maybe more interesting would be second example, which is that the vectors 2, 1, -1, 0, 3, 3, and 1, -1, 1 are all orthogonal. To see that, we'll just take some dot products. I'm going to write it as, 1.2, like the first vector, okay. We'll be careful. We'll call the first one A, the second one B, and the third one C. Then A dot B equals A dot C equals B dot C equals 0. You can check this. It's pretty, 0. It's pretty straightforward. Anyway, just do a dot product. And, okay, we'll do the first one. 2 times 0 is 0. 1 times 3 is 3. 1 times -3 is -3. -1 times 3 is -3. And 0 plus 3 minus 3 is 0, right? And it'll work for all of them, okay? So we have the first theorem, which is theorem 5.1, which says that every orthogonal set of non-zero vectors in Rn is linearly independent. So non-zero here, the 0 vector is orthogonal to every vector in Rn, because take its dot product with anything, you'll get 0, right? So, okay, so we're asking, and also the 0 vector, if it belongs to any set, that set is automatically linearly dependent. So, okay, let's ignore that one. And instead, let's do non-zero vectors. So the proof is kind of cool. So we just take, suppose you have scalars. Suppose there are scalars. This is not an assumption. We can always find scalars such that C1 V1 plus C2 V2 plus all the way up to CK VK equals 0. So let me just tell you what some of the assumptions are for this equation that I've written down. The scalars in question are the CIs, and we're assuming that V1 up through VK is an orthogonal set of vectors. So every single one of them is at right angles to every other one in the set. Also, all of them are non-zero. And when you do see, when you do this linear combination, you get the zero vector. So this is all the assumptions that go into this equation, but it's easier to say them than to write them, especially since this is a lecture video. Okay, and so now we do the following amazing trick. Compute this expression. That is a linear combination of vectors. So in particular, it's a vector. Actually, it's the zero vector. Dot vi. And I'm not even specifying which I. So we're going to take one of the vectors in the set. I don't care which one. If you want to work this with the example here, you can literally do any vector. Any vector in the set will work here. Okay. Do the dot product of one of your vectors with the entire linear combination. Well, that is precisely, of course, 0 dot vi, which is just 0 dot product, right? However, we know that the dot product is distributive. So in other words, this is vi dot v1 times c1 plus vi dot v2 times c2, and so on, all the way up to vi dot vk times ck. But vi dot vj, I'll just write, since vi dot vj equals 0 for j not equal to I, this says that like every single dot product is going to be 0, except for ci vi dot vi. That is the only that's the only term in the expansion. When you distribute the vi dot product, the only term that doesn't immediately go to 0 is this one. But the whole expression is still equal to 0, right? And so this one expression is the one that we need to show is equal to 0. But vi was assumed to be non-zero. Remember that? And so vi dot vi is also not 0. That's a property of dot products. And so it must be that ci times some non-zero number equals 0. That tells us that ci equals 0. But we didn't specify which I that we did. In fact, this will hold no matter which one you do. So every scalar is 0. In other words, the only linear combination of your vectors, your orthogonal vectors, which gives you the 0 vector, is the trivial linear combination. So in other words, the set is linearly independent. Pretty nifty proof. Okay. Knowing that you have a linearly independent set, take its span, you create a subspace. So if you took an orthogonal set, the span of an orthogonal set to get a subspace, then you actually had a basis for that subspace. And so we actually give a definition for that. We just say that an orthogonal basis for a subspace W of Rn is a basis for W, which is an orthogonal set. In other words, it's not enough to, a basis is just a linearly independent spanning set. Now we want an orthogonal spanning set. So, but orthogonal implies linearly independent, right? So, okay. So let's find an orthogonal basis for this subspace W. This is a plane, right? It's a plane in R3 subspace. Oh, passing through the origin, of course, right? Because 0, homogeneous linear equation in 3 variables. Okay, so Right. So the strategy here is notice that if so W is the set of vectors such x, y, z such that x minus y plus 2z equals 0. So x is really just y minus 2z. In other words, W is y minus 2z, y, z, these vectors, that whole set, where you can have any values for y and z, real numbers. So this is going to be the span of, well, if you can have any number for y, you'll have the vector 1, 1, 0. And if you can have any number for z, then the other vector is going to be negative 2, 0, 1. Great. This is two linearly independent vectors forming a basis for W. But they are not orthogonal. You can check that by doing a dot product. Their dot product is negative 2, not 0. So, okay, there is a general process for finding an orthogonal basis. It's called Gram-Schmidt orthogonalization, and that is the topic of 5.3. For now, we're just going to use brute force. So notice the dimension of W is 2. A set of two vectors is orthogonal if their dot product is 0. Orthogonal automatically implies linearly independent, so we just need to find another vector which is orthogonal to one of these two, and that will then the two vectors, one of these, whichever one it's orthogonal to, and the other vector, or I guess and that vector, will form a basis for W. So we just have to find one. So suppose this is the strategy, and for now this is all we've got. So suppose x, y, z is orthogonal to we'll do the first one. Should we do the first one? 1, 1, 0. Well, sorry. If that's true, then their dot product x, y, z dot 1, 1, 0 is 0. In other words, x equals negative y. Let me tell you where this came from, right? The dot product is just x times 1, right, plus y times 1 plus z times 0 equals 0. But x plus y equals 0. But then x is equal to negative y, right? Also, so since x equals negative y, and x, y, z is in the plane W, we also have x minus y plus 2z equals 0. Obviously, we have to be inside the plane, right? And so, but now we have a system of two equations. So we can go and solve. This x equals negative y is the same as x plus y equals 0. However, when you substitute x equals negative y into our second equation, you end up with negative 2y plus 2z equals 0. So y equals z. So if x equals negative y, then y equals negative x, and y equals z, and y, of course, equals y. So we can write the vector as negative y, y, y. For any value y, this will work. Any multiple, of course, for any value y, this vector is definitely inside of w. You can go and check that against the equation for vectors inside of w. But also for any vector inside of for this vector to be orthogonal to 1, 1, 0, the dot product has to be equal to 0, which just means that the signs of the first two numbers have to have the same number but opposite signs, which they do. So let's use 1, 1, 0. Negative 1, 1, 1. Sorry. Negative 1, 1. Negative 1, 1, 1. Okay, this vector is orthogonal to 1, 1, 0, and it is inside the plane W. So the basis, I'll just put W equals the span of 1, 1, 0, like we had, and now negative 1, 1, 1. We'll have a much better process for this come 5.3. In fact, a process that works anytime. So, yeah. One consequence of this, by the way, is that the coordinates of a vector with respect to some orthogonal basis are going to be very, very easy to compute. Consequence of just having an orthogonal basis. That's actually stated as the next theorem, and it's a very nice theorem. Basically says, okay, suppose you have an orthogonal basis for a subspace W in Rn, of course, and let little w be some, the unique linear combination of the basis vectors and so on, right? Okay, we can compute the scalars of that linear combination, which are the coordinates of w inside of big W, by just doing a dot product. Okay, Ci, so the ith scalar is just going to be w dot vi divided by vi dot vi. That's a number. It's a quotient of two scalars. The denominator will not be 0 because a basis is a linearly independent set, which means all of the vectors inside of it are non-zero. And so the dot product of two non-zero vectors is non-zero. And so, yeah, but more importantly, how do we get this number? Well, it starts with w is equal to this thing. So w dot vi, let me duplicate that again. If you take vi dot w, that's vi dot this thing. But just like in the previous theorem, when you take vi dot some linear combination of orthogonal vectors, well, since they're orthogonal, the dot product is just going to return 0 for every term, except for when you do vi dot with itself. So in other words, vi dot w is ci vi dot vi. Okay, divide both sides by that number. And we're done. Isn't that great? Orthogonal vectors make computations really easy. We have to work hard to get them sometimes, but then once we do that, we have no problem making use of them. They get some really, really nice properties. So for example, let's find the coordinates of 7, 3, 2 using the basis for the subspace that we computed in the last example. So Sorry, the first example. Because this is a two-dimensional subspace. Well, let's do it for this one. That's fine. This is different from what the book said, but okay, let's just check to make sure this is inside the vector space or the subspace in the previous example. So let's just write the defining equation. X minus y plus 2z equals 0. 7 minus 3 plus 4. Okay, this should be a negative 2. Minus 4 equals 0. 7, 3, negative 2. Let's just double check that's the right equation. X minus y plus 2z. Yeah. Okay, great. Just that's what we get for making up our own examples, right? Okay, so we don't need this. We want to find the coordinates of w with respect to our previous basis. So our basis was 1, 1, 0 and negative 1, 1, 1. We want the coordinates of w. Okay, w, we'll just call these u and v. W dot u it's a dot product, right? Oh, w dot u divided by u dot u, of course. That's what the formula from the previous theorem says. U dot u is just the number 2. U dot w is 7 plus 3, which is 10. 10 divided by 2 is 5. And w dot v over v dot v, well, v dot v is 1 plus 1 plus 1 is 3. And w dot v is negative 7 plus 3 minus 2. Negative 4 minus negative 6. Negative 6 divided by 3, negative 2. We even got whole numbers. That's amazing. Okay. And by the way, if you remember, we can write the coordinate vector of a vector with respect to a given basis. I'm just going to write it like this. And it's just the entries. We have to have an ordered basis, which we do, apparently. You can write our answer this way if you'd like, or w equals 5 times 1, 1, 0 minus 2 times negative 1, 1, 1. Actually, let's go and just verify that. 5 plus 2 is 7. 5 minus 2 is 3. And 0 minus 2 is negative 2. So, yeah, this is kind of a fantastic result. Look at how easy, we don't have to solve a system of linear equations to find these coefficients anymore. Just do a couple dot products, and it works out. Okay, so now we're going to take the nice properties of orthogonal bases and upgrade them to something called orthonormal bases. So an orthonormal set or an orthonormal basis of vectors in Rn is an orthogonal set or an orthogonal basis of unit vectors. The norm of a unit vector is equal to 1. So not just vectors that are all pairwise orthogonal, but also vectors of length 1. So when that happens, here's the characterization of an orthonormal set. If you have an orthonormal set Q1 up through Qk, and you do Qi dot Qj, you will either get 0 if the two vectors that you just dot product are different, or if you dot product a vector with itself, you get precisely the number 1, because the norm of a vector is the square root of the vector dot product with itself. But if the norm is equal to 1, then the dot product itself is equal to 1, right? Square both sides of this equation. Okay. Right. So, we want to show that this set is orthonormal. We have to do 3 dot products. So I'm just going to write these as u and v because you know how it is. Okay, we need to do u dot u. This is not as straightforward as just showing orthogonal. We have to also show, we have to show that it's orthogonal. Okay, let's do that first. Very easy. U dot v. So this is negative, negative 6 over 15 plus 4 over 10 plus 0. But 6/15 is 2/5, negative 2/5, right? Negative 6/15 is negative 2/5. 4/10, also positive 2/5, plus 0 is equal to 0. So that's good. So we're done, right? No, that shows that the set is orthogonal, right? All the vectors in the set, all 2 of them, are at right angles to one another. But we have to show that u dot u is equal to 1. Well, u dot u is 9 over 25 plus 16 over 25, which is 25 over 25, Pythagorean something. And v dot v is 4 over 9 plus 1 over 4 plus the square root of 11 squared over 6 squared. 11 over 36 apparently. 4/9 is 16 over 36. 1/4 is another 9 over 36. 16 and 9 is 25. Plus 11 is 36. 36 over 36 is equal to 1. Wow. Oh, I hope you like doing common denominators of fractions. That's the price we have to pay for orthogonal or orthonormal bases. Okay, so in the very first example of an orthogonal basis or orthogonal set, we had an orthogonal set of 3 vectors. It was these 3 vectors. We want to construct an orthonormal basis out of these 3 vectors. Okay, this is going to be fun. So notice that all 3 of these, okay, we've already checked orthogonal. We haven't checked ortho, we have to normalize. Okay. I think we've talked about this. Normalize a vector. Yes, we have talked about this. Compute, in fact, wasn't this an exam question? Maybe it was a homework question. I'm not sure. But we have to compute v over norm of v. That's it for each of these vectors. Right, because so v over norm of v is like, let me write it a different way. The norm of v is a number. It's the length of the vector. If I scale the vector down by its length, what have I done? I've shrunk it or grown it, whatever, so that it is a unit vector in the same direction as v. So really, we're computing this scalar multiple of the vector v. Which one is v? They're all v. Do it for all of them, because an orthonormal set is a set of orthogonal vectors, which this is, that are all unit vectors. In fact, you should probably have the definition. If you're going to memorize a definition, I would memorize an orthonormal set is an orthogonal set of unit vectors. That's the right way to say it. So, okay, we'll do the first one. Okay. I'm just going to write like this. Okay. Let's see. The norm of the first one is this. So the norm of a vector is the square root of the dot product with itself. Dot product of the first vector with itself is 4 plus 1 plus 1 is 6. Square root of 6. So we have to divide every entry in the first vector by the square root of 6. 2 over root 6. 1 over root 6. Negative 1 over root 6. Okay. The next one, I think the next one's also root 6. 3 squared, no. 3 squared is 9. 3 squared again is 9. 9 plus 9 is 18, so the square root of 18 is what we have to divide everything by. But fortunately, root 18 is 3 root 2. But if we're going to divide 0, 0, 3 by 3 root 2, the 3's cancel, and we're just computing 1 over root 2. So 0, 1 over root 2, 1 over root 2. And then the last one, the dot product of this thing with itself is 3. So square root of 3 is what we're dividing through by. 1 over root 3, negative 1 over root 3, 1 over root 3. Okay, I keep saying that orthogonal or orthonormal bases are amazing. And here I am looking at what some actual orthonormal or what an actual orthonormal set, in this case it's an orthonormal basis of R3, looks like. And now it's like, okay, that's a terrible vector and I don't want to work with it. Okay, but hear me out. So let Q1 up through Qk be an orthonormal basis for the subspace, for some subspace W. Then for every little w, the representation like this, w dot q1 times q1 and w dot q2 times q2 all the way up to w dot qk times qk, that representation is unique. Why? Because I could have written it as c1 q1, c2 q2, all the way up to ck qk. That we already know is unique. But I also have a formula for each of the CIs, and it's literally w dot qi. That's it. And every single time, it doesn't matter what orthonormal basis you have, w dot qi is the scalar that you use to compute, is that scalar for the linear combination of the qi's that produces w. The proof for this, by the way, is just theorem 5.2 again, but with the additional observation that the denominator, ci equals w dot qi over qi dot qi. But with the observation that the denominator is equal to 1. It's even easier than the other one. So like computing the coordinates of a vector given an orthonormal basis in some kind of subspace is literally just several dot products in a row. It's pretty nice. Okay, and we can do better. So we're going to talk about orthonormal matrices. So a square matrix whose columns form an orthonormal set is what we're going to call an orthogonal matrix. Did I say orthonormal matrix? Orthogonal matrix. It's because there's no real sense in working with like a matrix whose columns are all orthogonal. However, if the columns are orthonormal, that matrix has some really nice properties. And so we give it a definition that's an orthogonal matrix. So, for example, a matrix is orthogonal if and only if Q times Q transpose is the identity. That's true even if like Q is an m by n matrix. Just go and take the transpose. Okay, if it's an m by n matrix, then you have to check both directions of multiplication. It'll be I guess if Q is m by n, then Q transpose is n by m, and then it'll be im in that case. But literally just go and compute this, because notice that the columns, okay, the columns of Q are the rows of Q transpose, but if Q transpose is on the right, yeah, maybe I said that backwards. Okay, the rows of Q make up the columns of Q transpose, but if Q transpose is on the right, when you're doing multiplication, you take the columns of Q transpose and multiply them by the rows of Q. But every time you're going to get just one, right? Because that's like the columns of Q. Maybe I have this written backwards. I might have this written backwards. Yeah, it should be Q transpose times Q. Matrix multiplication order matters. But if you look lower down the page, you're going to see it doesn't matter. But okay, Q transpose times Q. There we go. Columns of Q times rows of Q transpose. But the rows of Q transpose are the columns of Q, which form an orthonormal set. In other words, the only time that you're going to get a non-zero number by taking that dot product is if you're taking a row I of Q transpose with column I of Q, which is a dot product of a vector with itself, but it's a dot product of a unit vector with itself. So the answer is 1. And so you're left with 1s on the diagonal and 0s everywhere else in your product matrix. And that is, by definition, the identity. Yeah. I only wanted to talk through that theorem rather than actually like write it out. But if you wanted to like literally write out, some columns for Q and then look at, those are the rows of Q transpose and then do the product. Yeah. That combined with the characterization of an orthogonal set, right? It's like, it gives you the identity. Anyway. But notice, wait a second. If Q is orthogonal, it's square. It's a square matrix. And apparently, there's another square matrix where when you take the product of the two square matrices, you get the identity. Okay, then that means you've just gone and found the inverse of that matrix. In other words, an orthogonal matrix, is orthogonal if and only if its transpose is precisely its inverse. That's quite a bold statement. In other words, in this example, if we had made the matrix whose columns are these three vectors, square roots all over the place, terrible. You want to find its matrix, its inverse, take its transpose, and you're done. Imagine trying to, I dare you to go and find the matrix inverse of this 3x3 matrix by doing row reduction. You should, at the very end, come to the conclusion that like the inverse of this matrix, the one where these are its columns, is the matrix that you get when you take the transpose of each of these things, row vectors, whatever, as the rows of that matrix. Just do the transpose. Yeah, it's amazing. This is like the ultimate. Okay, anyway. So for these two examples, I guess there's a proof that we should talk through. No. Theorem 5.4. Just look above, right? Product is the inverse. Yeah. Or product is the identity, which means that it must be the inverse. Okay. So for this example, we're going to verify that we're looking at an orthogonal matrix, and then go and compute the inverse. So how do we verify that it's an orthogonal matrix? We have to check that the columns form an orthogonal set. Okay. Well, the columns of A are definitely unit vectors, because take the dot product of each of those vectors with itself. You'll get 1. Okay. And we also have to ask that it's an orthogonal matrix, or that they form in an orthogonal set. So we have to take the dot product of every vector, every column, with every other column. So let's do these two. Dot product is 0. Nice. Let's do these two. Dot product is 0. Nice. And the last two. We could just do this by inspection, right? Just, oh, wow. At no point do you even get a non-zero number in the sum that makes up the dot product. So there we go. It's an orthogonal matrix. Compute the inverse. And let's write it over here. The inverse of an orthogonal matrix is its transpose. So that means we flip across the main diagonal. Right. You just do like this. So we're done. You could do it with row reduction if you really want, but like don't, because it's an orthogonal matrix. It's pretty great. And definitely don't try that with this thing, right? With this next one. So verify that it's an orthogonal matrix. Okay, now we actually have to do something. So first of all, cosine theta, sine theta. Let's call this one U. Oops. And V, we'll do the other one, negative sine theta, cosine theta. So we actually have to do some work here. U dot U is cosine squared theta plus sine squared theta, which is 1. Great. V dot V, this is, okay, V dot V is the same. Negative sine squared, like negative sine theta whole squared, which is just sine squared, plus cosine squared is 1. Okay. And U dot V, that's negative sine theta cosine theta plus cosine theta sine theta. Fortunately, those are the same number no matter what theta is, so you get 0. And since there are only 2 columns, there we go, the columns form an orthogonal set. An orthogonal set of unit vectors. So, okay, in other words, this matrix is an orthogonal matrix, which means that its inverse is equal to the transpose. But the transpose of this matrix just means take the minus sign that's in front of the sign x in the top right corner and put it in front of the sign that's in the bottom left corner. So let's just write that. Cosine theta, sine theta, negative sine theta, cosine theta. We've actually computed this inverse, at least kind of, right? This is a rotation matrix. And if you want to rotate, this is counterclockwise rotation by an angle theta. If you wanted to do the inverse, you rotate clockwise by an angle theta, but cosine is an even function and sine is an odd function. So you plug in negative theta, but instead of doing negative theta, just use the properties of even and odd functions, and the minus sign pops out for the sines and it goes away for the cosines. So this is the matrix that you get. That was a geometric argument, but also probably you can do it by row reducing with the identity. Okay, definitely. I just have never done it. By the way, there's a name for this type of matrix. It's called an isometry. It's not this type of matrix. It's the linear transformation that comes out of the matrix transformation, whose standard matrix is this guy. And the idea is an isometry is something like the METR is like, metry, whatever, is comes from the root word same as metric, which has to do with measurement. And of course, what measurement do we have in our vector spaces? Just Euclidean, like norm, length, whatever. And sure enough, an isometry is a linear transformation that preserves the notion of length, or preserves all lengths involved. In an R2, you've got 2 options. You've got a rotation through the origin about some angle, and a reflection across some line through the origin. So isometries they make up an interesting study. Okay, so we have some properties of orthogonal matrices, and then we'll call it. So let Q be an n by n matrix. We have the following are equivalent. If Q is orthogonal, or the norm of Q times X is the same as the norm of X. In other words, orthogonal matrices always preserve length for every X in Rn. Or if you have Q times X dot Q times Y, that's the same as X dot Y. So in other words, orthogonal matrices preserve dot products. You had X dot Y originally, then applying Q to X and Y, you preserve the dot product. That's like, it looks like this. If here's X, I don't know, and here's Y, and you want to do their dot product, it's like dot product is going to be like computing some, well, anyway, so yeah. Basically, by doing a rotation or maybe potentially a reflection, that work. Hopefully that was convincing. Doing some kind of rotation or reflection doesn't preserve the geometry surrounding those vectors. That's the properties. These are the properties that orthogonal matrices preserve when viewed as like linear transformations, right? Okay, one awesome other property is that the rows of an orthogonal matrix also form an orthonormal set. That's just by taking the transpose, which is the inverse. You're going to end up with just by tracing through the properties of inverse matrices. Those apply to the transpose of your orthogonal matrix. But the rows of the transpose are the columns of the original, or maybe I said that backwards. The rows of the original are the columns of the transform. And so the rows of the original orthogonal matrix also form an orthonormal set. Some more properties of orthogonal matrices. The inverse is orthogonal. That's kind of, we haven't said it yet, but like, come on, you know, right? When you know, you know. Also the determinant, okay, so the determinant of an orthogonal matrix is plus or minus 1. This is an interesting property, but it'll either be 1 or negative 1. Okay, also, for similar reasons, the absolute value of every eigenvalue of your orthogonal matrix is 1. That's the same as saying all eigenvalues of orthogonal matrices are 1 or negative 1. Okay, and the last one is that the product of two orthogonal matrices is again orthogonal. So you could think of that as, the easiest way to think about that is geometrically composing two linear transformations whose standard matrices are orthogonal matrices. You're going to preserve all your dot products, and then you're going to preserve all your dot products again. That's the easiest way to think about that. So that's it for this video. Next time we're going to talk about orthogonal complements and orthogonal projections, and then we're gonna build up to a process for finding an orthogonal matrix in any situation. But I will see you in the next video.